Welcome to episode 2 in the What is Obesity series, where I explain the physiology of obesity. This is part 2 of a 10-part series on obesity, what it is, how it works, and why standard advice fails midlife women. I'm Dr. Gordon. I'm board certified in obesity medicine. In episode 1, I introduced the 4 drivers of obesity: genetic, neurological, environmental, and hormonal. Today, we're going to go deep on one mechanism that explains why obesity is a chronic relapsing disease. Your body defends fat mass actively, persistently, with multiple redundant biological systems. One of my patients put it simply: I got down to a weight that I really liked, and I was happy. And then the weight just started coming back. Your body maintains a preferred level of fat mass. This concept is called the set point. Kennedy introduced the concept of lipostasis in 1953, proposing that the hypothalamus regulates food intake in relation to body fat stores. Later work confirmed that adipose tissue actively signals the brain to regulate both energy intake and expenditure. Decades of research supports this. Every time fat mass drops below the set point, your body initiates a coordinated response to restore it. The response involves your hormones, your brain, your nervous system, and metabolism, all at once, all at the same time, all in the same direction. Hunger is controlled in your brain. Leptin is a hormone secreted by fat tissue. Its job is to tell your hypothalamus how much fat you're carrying. Now, normally this works as a feedback loop. Fat mass rises, leptin rises, the hypothalamus receives the signal, appetite decreases, energy expenditure increases, and fat mass comes down. But in adults with obesity, the signaling gets messed up, and it gets really messed up. Leptin levels in adults with obesity run 3 to 5 times higher than in lean adults. And lean levels in men average around 5 to 10 nanograms per milliliter. In women, lean levels are typically higher, ranging from about 7 to 17 nanograms per milliliter, depending on body composition. In adults with obesity, levels reach 30 to 50 nanograms per milliliter or more. The signal is loud, but the hypothalamus stops responding, and we call this leptin resistance. 3 mechanisms drive it. First, leptin's transport across the blood-brain barrier slows down. The signal is high in the bloodstream, but low in the brain. Second, eating a lot of saturated fat and sugar triggers inflammation in the hypothalamus, and this activates brain immune microglial and astrocytic cells. Once activated, they release pro-inflammatory signals, including interleukin-6 and tumor necrosis factor alpha. The environment around the leptin receptor degrades, and the signal gets just harder to read. Now, the third mechanism is intracellular signaling pathways downstream of the leptin receptor get blocked by proteins called SOCS3 and PTB1B. The result is fat tissue sends a signal your brain can't hear. Inside the hypothalamus, there's a structure called the arcuate nucleus, and it contains 2 populations of neurons that operate in opposition. Appetite is controlled through powerful neurochemical reactions. The first population is pro-opiomelanocortin or POMC neurons, POMC. These produce a molecule called alpha MSH, which activates melanocortin-4 receptors, stimulating them to suppress appetite and increase energy expenditure. When leptin is present and functioning, POMC neurons are active. The second population, AGRP and NPY neurons, these drive hunger, promote fat storage, and inhibit the POMC neurons. When leptin falls, these neurons activate. In human cerebrospinal fluid studies, adults with obesity show significantly lower POMC levels compared to lean individuals. After 6 weeks of caloric restriction, leptin drops, POMC drops further, and agouti-related peptide or AGRP in the blood rises, working against the POMC. The orexigenic or appetite-stimulating system activates. The anorexigenic appetite-suppressing system is suppressed, both at the same time. Neuropeptide Y, or NPY, co-expressed with AGRP, is one of the most potent hunger-driving peptides in the mammalian brain. It stimulates food intake, inhibits the sympathetic nervous system, and promotes fat storage. During caloric restriction, falling leptin and insulin drive NPY expression up. Gamma-aminobutyric acid, or GABA, co-expresses in these same neurons and amplifies the hunger signal through receptors in the paraventricular nucleus. The system is layered. Each signal reinforces the next. So, what happens when you restrict calories? Leibel, Rosenbaum, and Hirsch published data in the New England Journal of Medicine in 1995 that remains the definitive quantitative description of metabolic adaptation. What they did was they took adults with obesity and reduced their body mass by 10%, and then they measured the body's energy output. Total energy expenditure dropped by 8 calories per kilogram of fat-free mass per day in adults with obesity. Now, fat-free mass is everything that isn't fat: muscle, bone, organs, water. Most adults with obesity carry around 60 kilograms of fat-free or lean mass. So 8 calories times 60 kilograms, extrapolating that data, that's 480 calories per day gone without any change in behavior. Half of that came from the body burning less at rest. Half came from the body becoming more efficient during movement. The same walk burns fewer calories. The same workout costs less energy. The body finds 2 separate ways to compensate, and it uses both simultaneously. 480 calories per day is roughly the energy in one meal. So when you lose weight, your body reduces your daily output, even when you are doing everything right. Now, the 1995 data suggests the adaptation maxes out at about a 10% loss from starting body weight, but a later study by the same group found that non-resting energy expenditure continued to decline with further weight loss, so this may not be the full picture. Everything after that first 10% is maintenance of a system that tries to get you back to your starting weight or higher. Remember The Biggest Loser? Contestants arrived obese. They were put through extreme caloric restrictions and roughly 3 hours of vigorous exercise per day. Over 30 weeks, they lost a lot of weight, and the world watched the drama as trainers yelled at contestants in an effort to motivate them. The before and after images were everywhere, and they were striking. The message was clear: this is what happens when you commit and do the work. But then the contest ended, and everyone went back to their lives. Fothergill and his colleagues followed 14 contestants for 6 years and published the data in 2016. By the end of the competition, participants had lost an average of 58 kilograms or 128 pounds. Resting energy expenditure had dropped 610 calories per day. 6 years later, those participants had regained an average of 41 kilograms or 90 pounds, and their resting energy expenditure remained 704 calories per day below baseline. After adjusting for body composition and age, the persistent metabolic adaptation was 499 calories per day below the scientists' prediction. So they regained most of their weight, yet their metabolism was still burning nearly 500 calories per day below expected for their current body size. The contestants who lost the most weight had the greatest metabolic slowdown. The more weight they kept off, the harder the body pushed back. Now, the public narrative blamed the contestants, but here's what the science says. Kevin Hall was a senior author on the original Fothergill paper, and in 2022, he published a reinterpretation of the same data in Obesity, the Journal of the Obesity Society. He did not dispute the numbers, but he argued that the 499 calorie figure may be specific to Biggest Loser intervention. The combination of massive caloric restriction and 3 hours of vigorous exercise per day is extreme by any measure. There's not a lot of people who are going to do that. Under those conditions, the body may suppress resting metabolism to compensate for extreme sustained activity. And that's a different mechanism than typical weight loss alone, producing the suppression. The 499 figure is 5 to 10 times larger than data reported by other studies. So in more typical weight loss scenarios, metabolic adaptation runs around 50 to 90 calories per day. Martins and colleagues ran 2 controlled trials and found that metabolic adaptation was present during active caloric restriction. Once participants reached a stable weight, it decreased significantly. At 1 year, it was largely undetectable. Ostendorf and colleagues looked at people who kept weight off long term. And when they looked at the people who had kept weight off for years, their resting metabolic rates were normal. But the range across individuals was wide. So the question the research has not yet answered is whether the metabolic suppression is permanent or proportional. The Biggest Loser data says it can persist for 6 years. The Martins data says it decreases when you reach true energy balance. The Ostendorf data indicate that those who maintain weight loss do not have a metabolic penalty. The Obesity Society's 2025 Clinical Management of Obesity Guidelines states that the reduction in total energy expenditure appears to persist indefinitely for as long as a patient maintains weight loss. That language draws primarily on the Libel and Fothergill data and may not fully reflect the more recent evidence I've just mentioned. There is more room for research here. The fight your body puts up against fat loss is real. How long your body suppresses energy expenditure is an open question. We don't have that answer. Researchers with data on both sides have made compelling arguments. What is settled is the hormonal picture in sustained weight loss. Ghrelin, your hunger hormone, stays high. Leptin, your fullness hormone, stays suppressed. Peptide YY and cholecystokinin remain below baseline for at least a year after weight loss ends. Sumitran and colleagues documented all of this in 2011. Appetite remains high long after the fat is gone. Martins published data in 2023 showing that the degree of metabolic adaptation is directly coupled to increased hunger. The slower the metabolism, the stronger the appetite signal becomes. The two systems are coordinated. Metabolism may recover. The hunger does not resolve on its own. That is the clinical reality your body faces every time you lose weight and try to keep it off. The biggest loser contestants did not fail. We all watched in real time as their biology demonstrated the disease process of obesity. The cameras just happened to capture it all. So what about hormones? Sumitran and colleagues published data in the New England Journal of Medicine in 2011, following 50 adults through 10 weeks of a very low-calorie diet and then for a year afterward. After a mean loss of 13.5 kilograms, the hormonal data showed the following at 62 weeks. Leptin, the fullness hormone, remained significantly below baseline. Ghrelin, the hunger hormone, remained significantly elevated. Peptide YY, another fullness hormone, remained significantly suppressed. Cholecystokinin, which signals fullness and slows digestion, remained below baseline and showed a statistically significant but modest effect in the primary analysis. 9 appetite-regulating hormones were measured in total, and nearly all shifted in a direction that drives hunger and promotes fat restoration. Subjective appetite ratings also remained elevated at 62 weeks. So the biological drive to restore weight persisted for the year after weight loss phase ended. But can it be reversed? Well, Rosenbaum and Libel conducted controlled leptin replacement studies in subjects at reduced weight. Now, after 10% weight loss, resting energy expenditure, total energy expenditure, sympathetic nervous system tone, and thyroid hormone levels decreased, while skeletal muscle efficiency increased. The body became more efficient at movement and burned less while doing the same work. When leptin was replaced by injection to restore pre-loss circulating levels, these adaptations were at least partially reversed in studies by Rosenbaum and Libel. But in those studies, energy expenditure returned toward baseline, thyroid hormone levels recovered, muscle efficiency improved, and the heightened drive toward food cues decreased. Now, these findings come from small studies by a single research group and have not been independently replicated. So they should be interpreted with that context in mind, or like we say, taken with a grain of salt. When leptin was given to adults with obesity at their usual weight where leptin was already elevated, it produced no meaningful effect on weight across multiple randomized controlled trials. The body fights hard to prevent fat loss. It fights much less hard to prevent fat gain. That imbalance is part of how obesity develops and worsens over time. That's part of our evolution. So what about the clinical picture? A patient loses 10 kilograms. Her body responds with approximately 1,000 calories per day of appetite-driven biological pressure to restore that mass. Her hunger hormones are still shifted 1 year later. Her resting metabolism is running hundreds of calories below its pre-loss level. Her hypothalamus is interpreting her current weight as a state of deprivation. Her body thinks she's starving, but she's doing everything right. Her body is fighting against her. This is why it's so hard. Short-term interventions produce short-term results because the neuroendocrine biology does not resolve at the end of a weight loss intervention. The body still pushes hard to increase weight back to what it considers baseline. Treating the disease of obesity requires understanding its physiology. That's what I've just spent all this time explaining to you. Longitudinal individualized care is best. I'm board certified in obesity medicine. My practice focuses on midlife women with complex metabolic and hormonal disease. Before GLP-1 medications, treating obesity meant sustained behavioral intervention or surgery. Now, bariatric surgery is effective, but it results in clinically significant weight regain, defined as regaining at least 15% of lost weight. And this happens in approximately 25 to 35% of bariatric surgery patients. Newer incretin-based medications, particularly the dual GIP-GLP-1 receptor agonists, are narrowing the gap with bariatric surgery, and we've got even more in the pipeline. Some clinical trial participants are achieving weight loss in the range historically seen only with surgery. Oral GLP-1 agonists are now FDA approved for chronic weight management. The biology we just covered is exactly why these treatments work at the level of the brain, the hormones, and the metabolism. Now, this is episode 2 of 10 in the What is Obesity series. I know this was dense. Thanks for sticking with me. Understanding the biology is the first step. The next question is what to do about it, and that's what the rest of the series covers. Subscribe so you don't miss the next episode. In episode 3, I'm going to cover how the menopause transition changes each of these mechanisms and why the same body that was at the same weight for 20 years changes in midlife. And for more education grounded in physiology, not blame, join my Substack, drmichellgordon.substack.com.